Interference of waves. Principles of superposition for waves. It often happens that two or more than two waves passing simultaneously through the same region. When we listen to a concert, for example, sounds from many instruments fall simultaneously on our eardrums. The electrons in the antennas of our radio and TV receivers are set in motion by a whole array of signals from the different broadcasting centers. Y equal to Y1 plus Y2. We consider only two. Okay. Overlapping waves algebraically add to produce a result wave. This is another example of a principle of superposition, which says that when several effects occur simultaneously, their net effect is the sum of the individual effects. The principle holds as long as the amplitude of the waves are not too large in acoustic, optics, electromagnetism, quantum physics. Amplitude and not too much. Look at the two waves. They meet together. Okay, one from left to right, one from right to left. They intercourses and they separate again. Moreover, each pulse moves through the other, as if the other were not present. Overlapping waves do not in any way alter the travel of each other.
Here is a torsion wave of medium amplitude traveling left to right. Here is a wave of the same amplitude traveling right to left. We'll now send these waves in simultaneously to show what happens when they meet. The amplitudes add as the waves pass through each other. Then the waves continue on their way unchanged. Here is a torsion wave of medium amplitude traveling left to right. Here is a wave of the same amplitude traveling right to left. We'll now send these waves in simultaneously to show what happens when they meet. The amplitudes add as the waves pass through each other. Then the waves continue on their way unchanged. What will happen if the waves have equal but opposite amplitudes? The waves cancel momentarily, then pass on. This demonstration uses an Apple computer-based real-time spectrum analyzer consisting of a series of filters covering the entire 10-octave audio spectrum in 1/3 octave intervals. To indicate the calibration, the cursor will now be moved from 100 Hz up to 10 kHz with an audio oscillator set to each frequency. The top channel shows the total intensity of the signal. Using this analyzer, we can observe the groups of harmonics, called formants, associated with certain sung vocal sounds. Here is a male voice singing the vowel oo at a frequency of about 150 Hz. The frequency of the first formant is about 300 hertz, and the frequency of the second formant is about 800 hertz, so they overlap. Here is a male voice singing the vowel E at a frequency of about 150 hertz. The frequency of the first formant is about 300 hertz, as in the vowel OO, but the frequency of the second formant has risen to about 2500 hertz. The difference between the sounds OO and E is the frequency of the second formant. The second formant does not change significantly as the frequency of the voice changes for the same vowel sound.
Fourier analysis. French mathematician Fourier explained how the principle of superposition can be used to analyze non-sinusoidal waveforms. He shows that any waveform can be represented as a sum of a large number of sinusoidal waves of carefully chosen frequencies and amplitudes. Fourier's theorems tell us that every curve, no matter what its nature may be, or in what way it was originally obtained, can be exactly reproduced by superposing a sufficient number of simple harmonic curves. In brief, every curve can be built up by piling up waves. You can see now why we spend so much time analyzing the behavior of a sinusoidal wave. When we understood that, Fourier's theorem will open the door to all other wave shapes. Now, this is almost like trigonometric wave. Okay, it can be looked at as so many sinusoidal wave together. Okay, and written it can be write as minus sine omega t over pi, minus sine 2 omega t over 2 pi, minus sine 3 omega t over theta, and so on.
This Fourier synthesizer produces electrical signals of precise frequencies. It produces a fundamental frequency of 440 Hz. It can also produce harmonics of the fundamental at 880 Hz, 1320 Hz, 1760 Hz, and higher frequencies. We can select harmonics to add to the fundamental with amplitudes and phases we choose. The sum of all the signals we select are displayed on this oscilloscope and speaker. Here is the fundamental at 440 Hz. We'll now add the second harmonic at 880 Hz. Notice how the sound changes. Now we'll take away the second harmonic and add the third at 1320 Hz. Here is the fundamental with the ninth harmonic at 3960 Hz. Now we'll add together a specific combination of fundamental and harmonics to make a square wave. Here is a different combination which makes a triangular wave.
Interference of waves. Suppose we send two sinusoidal waves of the same wavelength and amplitude in the same direction along a stretched string. The superposition principle applies. What resultant wave does it predict for the string? The resultant wave depends on the extent to which the waves are in phase, in step, with respect to each other. That is, how much one waveform is shifted from the other waveform. Now this is a one waveform shift from other waveform, okay? Yeah. We put them together and we get this time of three. Actually, you can see look at some intensity. This is a positive, this is negative, and this is a little bit left. So the final resultant is this one at this point. This curve is made from this way, okay? They put them together. If the waves are exactly in phase, so that the peaks and the valleys of the one are exactly aligned with those of the other without any shifts, these two are exactly overlapped, okay? And in this point, the amplitude is double, okay? This double, okay? Now, they combine to double the displacement of either wave acting alone. If they are exactly out of phase, the peak of the one are exactly aligned with the valleys of the other. Now, okay? And then we see some instant exact the same, so zero. See, the resultant is zero. Okay? They cancel out everywhere, and the string remains straight. We call this phenomena of combining and cancelling of wave interference, and the waves are said to interfere. These terms refer only to the displacement of the waves. The travel of the waves is unaffected. They're going on, traveling, okay? Only affect displacement of the wave. So, suppose y1, this is the first wave, ym sine kx minus omega t, and y2, x2 is ym sine xt minus k plus phi. You see what? Compared to these waves, they have the same amplitude ym, same speed omega over k, same wavelength lambda because k is the same. K lambda equal to 2 pi. K is the same, lambda is the same. Same frequency omega. So they have same period and same direction, because it's minus sign. Okay. But different phase constant phi. This is 0, this is phi. They're only that difference. And suppose they meet somewhere, we see the interference between them. Okay. Put them together, and the sum of them is the result. Let me do some exercise. Okay. We put y1, y2 inside. Okay. y1 equal to ym sine kx minus omega t. Okay. y2 is ym sine kx minus t. Okay. And then we have ym in comma. We take it out. Okay. We get a sine alpha plus sine beta. Okay. We know sine alpha plus sine beta in trigonometry. Sine alpha plus sine beta equal to 2 sine half alpha plus beta cosine half alpha minus beta. We put this as alpha, this is a beta. So sine alpha to beta, okay, and divide by 2. So you have this one, kx minus omega t plus half theta. Okay, and the cosine, you minus this one 2, you get a phi. Have 2. So the result is 2my cosine half phi sine kx minus t plus half f. The result. Let's look at the result wave. It is still a traveling wave with the same k, same omega, same direction, same velocity, a little bit different phase. And their amplitude changes. the amplitude changes depends on the phi. Okay? If phi is 0, they are in phase instead. Cosine 0 is 1, so you get y equal to the maximum amplitude of 2y. If the phase is 180, and then we say cosine 90 degrees is 0, you get 0. Okay, that's called out of phase. Okay. Now we have these two. We get this one. Let me re-emphasize it. This is the final component wave. It's still a traveling wave. Okay. It's still traveling with the same velocity, the same lambda, or some frequency, a little bit different phi. But the amplitude changes, depends on the phase difference between these two. Okay, okay. So maximum is 2m, minimum is 0, depends on the phi. If two sinusoidal waves on the same amplitude and wavelengths travel in the same direction along a stretched string, they interfere to produce a resultant sinusoidal wave traveling in that direction too. Okay. The resultant wave differs from the original waves in two respects. One, its phase constant is half phi. And two, its amplitude y is 2ym cosine phi, depends on the phase difference. Now, if phase difference is 0, they overlap. We get maximum. Okay? 2m. If phase difference is 180, then shift halfway, they don't see any vibration. So the phi is 180, y equal to 0. And we have a between. Okay, this still propaganda transverse wave. Okay, with the same direction, same velocity, same wavelength, and so on, same frequency. Okay. Now, if phi equals 0, cosine 0, 1, they reach the maximum value 2mv. Interfering that produce the greatest possible amplitude is called fully constructive interference, phi equals 0. If phi equals 180, cosine 90 degrees is 0. The y prime m is 0, and we see no motion of string. This type of interference is called fully destructive interference. Everything destructive. Okay. Know that when the interference is neither full destructive or nor full destructive, it is called intermediate interference. The amplitude of the resultant wave is then intermediate between 0 and 2ym. A phase difference phi equal to 2 pi radius corresponds to a shift of one wave relative to the other waves by a distance of one wavelength. So phase difference can also be described in terms of wavelengths. Now you look at this one. For example, this one too is shifted by 0.5 wavelengths, and they are out of phase. Okay. 2 pi phase difference equals 1 wavelength shift. Okay. So if they overlap, okay, the delta phi is 2 pi, or lambda is 1 lambda. So we get 2 pi phase difference equal to lambda shift. Okay, lambda change shift. Okay. That's very important. So in this case, two waves, their delta L equal to m lambda. 1 lambda, 2 lambda, 3 lambda shift phi. This one is m lambda plus half lambda. Okay, m can be 0, 1, 2, 3, 4 shift. They are the same. Okay. Two waves with the same wavelength are in phase. If their phase difference is 0, or any integral number of the wavelengths. Thus, the integral part of any phase difference expressed in wavelength may be discarded. For example, a phase difference of 0.40 wavelength is equivalent in every way to one of 2.40 wavelengths. And so, the simpler of the two numbers can be used in computations.
We'll use this ripple tank, which projects an image of waves on the surface of water, to show interference of waves from two closely spaced slits. When we put a pair of slits in front of the waves, an interference pattern results. Decreasing the wavelength increases the number of nodal lines in the pattern. This split-screen view shows the patterns resulting from the two wavelengths. Increasing the separation of the slits also increases the number of nodal lines. This split-screen view shows the patterns resulting from the two slit spacings.
Sample. Two identical sinusoidal waves moving in the same direction along a stretched string interferes with each other. The amplitude Ym of each wave is 9.8 millimeter, and the phase difference phi between them is 100 degrees. Question A. What is the amplitude Ym of the resultant wave due to the interference of these two waves? And what types of interference occurs? It's simple. We just put in the formula. Okay, Yn prime equal to 2Yn cosine phi. Okay, and the phi is 100 degrees, so we put Y. This is Ym is 9.8. When we put a number, we should use the standard unit, meter. So this is 0.0098 meter. We get Y prime. Okay, it's 0.013, 13 millimeter. Okay, getting a little bit larger. Okay, it is intermediate interference. Question B. What phase difference in radius and wavelengths will give the resultant wave an amplitude of 4.9 millimeter? We also use the formula. This one is 4.9 millimeter. It should be equal to this one. We want to find this phi. So we put in sign. Okay. We can find the cosine phi. Okay. Now, you have this one. We only pick up the one to suit our purpose. Okay. And then we put this one, the phase difference, and we put the lambda. So it's about 0.42 lambda. Okay. This is a phase difference 2.6 radio, equivalent to 0.42 lambda. Phasors. We can represent a string wave or any other types of wave vectorially with a phasor. In a sense, a phasor is a vector that has magnitude equal to the amplitude of the wave, and that rotates around an origin. The angular speed of the phasor is equal to the angular frequency omega of the wave. Now we look at this one. This is the phasor, can represent a wave. Okay? And we define, in this book, we define counterclockwise is the positive direction omega. Okay. Now, look at this. Here is minus omega. Okay. So as the phasor rotates around the orange at angular speed omega, okay, its projection y on the vertical axis varies simultaneously from a maximum Ym, so 0, to a minimum of minus Ym. This variation corresponds to the sinusoidal variation in displacement Ym of any point along the string as a wave passing through it. Now, this one is go direction because it's minus omega. Positive direction, this one is minus, go this direction. And its projection on the vertical line is the y1. y1 equal to ym. This angle is called kx minus omega t, y, and 1, get this one. Okay. When two waves traveling along the same string in the same direction, we can represent them and their result wave in a phasor diagram. This is y1, okay, equal to y1m sine kx minus omega t. Okay, this is y1. Okay. And then we have y2. Y2 is y2m with the same direction, same wavelength, same frequency, only different phase. So this y2 is this one. Why? This phase is positive number, is counterclockwise. So it faces this one. We put them together. And in phasor diagram, with this vector, okay, we put it E, the same vector, and we find the sum of these two, we get this one. This is y prime, the sum, resultant wave vector, okay? And it has a beta angle with the first one, okay? The first one is 0, okay? First one, okay? So what we do, we look at this one, because the E are the same. So this is equal to this one. So this beta angle equal to this beta angle. And this phi is what is? Phi is the angle between the first one and the second one. This is phi. Okay? That's phi. So which is that this y1 equal to y12 equal to ym. Then because the y with the ym prime, with the resultant y is what? So we take this from beta equal to half phi. y1 is equal to 2 this length. Each this line equal to y1m cosine beta. So y1m equal to 2 ym cosine beta. Beta is half theta. Okay, and then we see the result are the same as we do in above calculation. Okay. So finally ym equal to yn prime. Okay, sine kx plus c. Exactly the same answer. This time we do from the phasors, vector phasor. In case y1m equal to ym to y, beta equal to half theta, and we know the resultant was equal to Tym plus c, the amplitude. Okay, and you got this one. Is the answer. Okay. Know that in contrast to the above methods, using phasors allowed us to combine waves even if their amplitude are different. In above calculation, algebraically, we have required these two are the same, but with a phasor, they cannot be. They can not different. Okay, I'm sorry. Know that in contrast to the above method, using phasors allowed us to combine waves even if the amplitude are different. These can be different. Two solenoidal waves, y1 and y2, have the same wavelength and travel together in the same direction along the string. The amplitude are y1m 4.0 millimeter and y2m 3.0 millimeter, and their phase constant are 0 and pi over 3, respectively. What are the amplitude ym prime and phase constant beta of the resultant wave? Write the result wave. Now, this is a phasor, the vector. We treat them as a vector. Okay, we move the second one to here. We find the sum y1m. This is the result of the wave. Okay. This is 3 over the pi. How do we find? This is as usual. We divide it into x direction, y direction. Okay. So y prime horizontal, y direction, equal to this horizontal, this cosine theta. Okay. This horizontal. Okay. And this one horizontal. Y2m cosine pi. Okay, and we put the number inside. We take the millimeter as a result. Okay, and y vertical is, this vertical is 0. This 90 sine theta is 0, and this is a sine pi over 3. Okay, and we get this number. Once you get a 2 component, we get y. Ym is the square root of this and this square. Okay, we get the answer. And the angle is tangent beta equal to vertical of horizontal. Y of x is 2.60 over 5c. We get the beta. So finally, we can find the answer equal to c. Y prime equal to magnitude 6.0 millimeter sine kx minus c plus 0.44 radius. That's it.